Okay, chemistry class. This is Mr. Mellinger. This is your chemistry assignment for Thursday and Friday. It's a little bit longer assignment, but you do have this solutions video, and I'm going to go through a lot of these problems with you. I'll leave a couple for you to do on your own, some for you to do on your own. This is day 52, 53. It's Thursday and Friday, and that's May the 7th and May the 8th. This is all due on Monday, May the 11th. And the late due for this, the latest you can turn this in, is Tuesday, May the 26th. Try to get it in by May the 11th because you get full credit. After May the 11th, it's somewhat reduced credit. Okay, so let's go ahead. This is kind of a lesson and an assignment put together in one. So we're going to deal with a subject called stoichiometry. What is that? It's a funny word. Stoichiometry is the study of conversions from the language of chemical equations to measures that we make in the real world, such as grams of solids or liters of gases. So it's how we work with a chemical equation. A mole is 6.022 times 10 to the 23rd. Usually this refers to the number of atoms or molecules. The chemical equation can be read as this. So here's a chemical equation to make water. We're not going to worry about the states. This is gas, and this is either gas or liquid, but we're not going to worry too much about that. It's just what is the chemical formula. It's like a recipe in cooking to make water. So what it's saying is you need two hydrogen molecules. You take two hydrogen atoms and put them together, they form a single molecule called a hydrogen molecule. You need two of those hydrogen molecules. And then oxygen, if you take two oxygen and put them together, they form an O2 or an oxygen molecule. That's two oxygen atoms put together. And hydrogen and oxygen, by the way, always form molecules. You never, in gas, find hydrogen just as H or oxygen just as O. It's always H2 and O2. Okay, so what this means is, if you read this equation, it says two hydrogen H2 molecules plus one O2 molecule will produce two H2O water molecules. So that's one way to read this. So what chemical equations deal with is number of atoms or number of molecules. They're not interested in how much the atoms or the molecules weigh or how much space they take up. They're interested purely in matching up numbers. Okay? So let me give you an example. If I have boys and girls in a class and I want to have groups of two, and let's just say for the sake of simplicity, I want to have one boy and one girl in each group, then what I'm interested in is getting one boy, one girl, matching them up and making a group out of them. I don't care that the boy weighs 200 pounds and the girl weighs 80 pounds, or that the girl weighs 200 pounds and the boy weighs 80 pounds. That's completely irrelevant. I'm just interested in matching up one boy and one girl. So I'm counting numbers of boys and girls when I make the group, not how much they weigh, how much space they take up, or anything else. It's the same with a chemical equation. It's interested in matching up numbers of molecules to make this many numbers of this many water molecules. Okay? So, now, molecules are really small. We can't work with two hydrogen or one oxygen molecule. They're too tiny. We can't see them, let alone work with them. So, what do we do to remedy that? Well, if we multiply everything in this equation by a really, really large number, 6.022 times 10 to the 23rd, we can read the same equation as, and that's called a mole. Then we can read this as 2 H2 moles plus 1 O2 mole, again, mole being that number, will produce 2 water moles, or 2 moles of water. Okay? So that gives us a big enough number of molecules that we can actually work with. We can actually see them in a lab. You can see a mole of water. It's visible. It's big enough for you to see. You can weigh it on a scale. So we need to use a really big number. We talked about earlier why they picked that really big number. It's not really important right at this second. It's just a really big number that we need to have so that we can actually see the hydrogen and the oxygen and the water. We have enough to actually see and weigh. So, and that's what I say here. We can actually see and weigh 1 mole of H2O. So the equation is speaking to us in amounts that we can use in the real world. Here's the problem with a mole. It's too big a number for us to count. So molecules and atoms are too small for us to see, but a mole, this number, is too big for us to count. we can't count a mole of molecules, H2 molecules, or a mole of O2 molecules. It's just too big. So we need to have a way to get between things that we can measure in the laboratory and this big number of atoms and molecules that we're going to be working with. So, down here it says solids. This is actually not true. It could be solids, liquids, or gases. But we still can't count a mole of atoms or molecules. So how do we know we have a mole? We do this by using the mass in grams of 1 mole of an atom or molecule. Here is the molar masses of some common molecules. So where do you get this? You get this off of the periodic table. So we talked about this in the last couple of weeks, that 1 atom of hydrogen is 1.01 atomic mass units. That's just about the mass of 1 proton. But that's too small for us to work with, so we found that if we multiply by this magic number 6.022 times 10 to the 23rd, we'll end up with the same mass, 1.01 for hydrogen, except it'll be in grams, not in atomic mass units. And grams is something that we can measure on a scale in a laboratory. So only that number will convert this from 1.01 grams to the exact same number, 1.01 atomic mass units, I should have said, to the exact same number of grams, which is 1.01. Okay, that's why this number is the particular number that they chose. It's a really big number, and it's the only really big number that converts from AMU to grams and gives you the same number. Okay, so 1 mole of hydrogen, that's 6.022 times 10 to the 23rd hydrogen atoms, is 1.01 grams. 1 mole of H2O is 18.02. How do we get that? Let's go ahead and do that calculation over here. We have hydrogen. We have 2 of them. They each have a mass of 1.01 grams. That equals 2.02 grams of hydrogen in 1 mole of water. For oxygen, we see that we have 1 oxygen atom, or 1 mole of oxygen, I should say, times 16.00. Where did that come from? Same place we got the 1.01. It's at the bottom of oxygen. So that's the number of the mass of an oxygen atom in atomic mass units, but if we multiply by 6.022 times 10 to the 23rd, it's the mass of 1 mole of oxygen atoms. Okay? 16 grams. So this equals 16.00 grams of oxygen. We add those two together, and we get the mass of a water molecule of a mole of water, and that's going to be 18.02 grams. Okay, and that's the number that's right there. Mole of CH4, let's go ahead and do that just so we get a little practice doing this. So carbon, there's 1 of those. You come over here, you find the molar mass of 1 mole is 12.01 grams. And then hydrogen, the formula says you have 4 of those. And again, we just looked it up. It's 1.01 grams for hydrogen. So that gives us 12.01. This gives us 4.04. And you add those together, and you get 16.05. And that's the mass of 1 mole. I had rounded it before, but it should be 0.5. Okay? Alright. So we see that there's a way to convert between grams, which is something we can measure in a laboratory, and moles, which is something we need to use a chemical equation like this. So this little diagram is meant to illustrate that. Because we can measure grams on a triple beam scale, that's what this is called, or triple beam balance, we can calculate the number of moles. So if we measure that we have 18.02 grams of water, let's just say that's the amount we measured, and we put it on this scale, we know that 1 mole of water is 18.02 grams of water. So now we know that we have 1 mole of water. If we have 18.02 grams here, that's 1 mole of water. So that's what the chemical equation understands. It speaks in the language of moles, and we speak in the language of grams. And so this is called the molar mass conversion. It's what you got off the periodic table. So to say that 1 mole of carbon equals 12.01 grams is called a molar mass conversion. It's like a translator. If you speak English and somebody else speaks Russian, you need to have a translator who speaks both English and Russian so that you can communicate with the other person and they can communicate with you. Well, we speak in the language of grams that we can measure in the lab. This chemical equation speaks in numbers of particles called moles. We can't count a mole of particles, it's too big. So we need this translator that converts between moles of a substance and how many grams it is. So this is the translator that allows us to communicate with the chemical equation. Okay, so we're going to solve some of these problems. And I'm going to ask you to do a little math here, okay? But I'm going to do it with you. So balance the following equations. Well, they already did that for you. It's the same equation we had on the previous page. State the molar mass of each molecule compound and answer the following questions. So I did 2 things for you. I didn't make you do on this one. I balanced the equation. This is the equation to make water out of hydrogen and oxygen. And I gave you the molar mass for each of these either molecules or compounds. Hydrogen is a molecule. It's not a compound because there's only 1 element. So H2. So what I want is the molar mass not of 2 H2s, but of just H2. And there it is. We just calculated that one a couple minutes ago. 1 mole of H2 is 2.01 grams of H2. Again, you got 1.01, and if you have H2, you have 2 times that, you have 2.02. Okay, oxygen, O2. Again, we only want the mass of O2. So we come over here, and a single oxygen atom is 16. So if you have an O2, that means you have 2 oxygen atoms stuck together. So that's 32. So 1 mole of O2 is 32 grams of O2. One thing I ask that you get in the habit of doing is writing the unit of measure, grams, and the substance. We're dealing with 3 different substances here, H2, O2, and H2O. So you always want to write what substance are you talking about. The other thing is what unit of measure, because here we're talking about grams, whereas on this side we're talking about moles. And moles should have been spelled without an E. That's typically the way it's done, but we'll leave it the way it is. So here we are. This is our world. There you are right there. And you're in the laboratory with one of those scales I just showed you, and you're measuring things in grams. You can weigh things in grams. But again, chemical equations don't speak in grams. They don't understand weight. Remember, they're interested in matching up molecules to make something else. They don't care that this molecule is really heavy compared to this one, which it is. They don't care about that. They just care how many of these you have and how many of these you have. That you have twice as many of these, that's the 2 there, for every one of these. You have 2 of these for every one of these. Even though this molecule is much heavier, they don't care about that. It has nothing to do with what we're doing. But what we do is by measuring the mass of each of these compounds, because we speak in the language of grams, and then we put it through our translator, the person that speaks both English and Russian, we can translate into the language that the chemical equation speaks in. Okay? So I've given you the translators here for all 3 of these compounds. And so what I'm going to do is give you some problems here, some questions. And what you do is use this. Think of this as a graphic organizer. And you're going to use this to kind of figure out how to do things. Now let me give you a hint. If it gives you a number of moles of one of these substances and wants you to convert with moles, then you start off inside the equation and you end in the equation. All you have to do is move from between these. That's moles to moles. What if it gives you a number of grams of one of these? Let's say hydrogen, and it wants you to it asks you how many moles of water will you get from that. Then you need to go from grams through your translator into the equation, and then across the equation, and that'll give you the number of moles of water. Okay? The most complicated one, and it's not that complicated, is what if they give you grams of H2 and they want you to tell them how many grams of water that you get. So you're going from our world in grams to our world in grams. There is no way you can go directly from here to here. You have to go through the chemical equation to get from here to here. So what you have to do is you have to go from grams to moles using the translator, go from moles over to moles, and then come back out using the translator for water back out to grams. So it's a 3-step process. Step 1, step 2, step 3. And by doing that, that'll tell you if they told you that you were given a certain number of hydrogen, moles of hydrogen, how much, or given a certain number of grams of hydrogen, how many grams of water could you produce? Remember, this chemical equation is a recipe. It's just a recipe. Unfortunately, the recipe is written in Russian and you speak English, so you need somebody to translate from what you understand into what the recipe speaks. And then once the recipe does its job and converts, then you need that translator to get you back out here. So let's see some number examples, and this will make more sense. How many moles of H2O can be made from 2.5 moles of O2? So what I want you to do is, it gives you a number and it gives you a how many or how much. So what I want you to do with the how many or how much is put a question mark in that box. So how many moles of H2O? So if we come up here, we're in the chemical equation. This is the moles area. This is chemical world. And it wants to know how many. So I'm going to put a question mark there. Can be made from 2.5 moles of O2. So I'm in the moles, I'm in the chemical equation, it's dealing with moles, so I'm in here, and it says that there's 2.5. So if they give you, assuming that you have enough hydrogen, you have to have hydrogen to make this work, assuming that they give you enough, they always assume you have enough of the other reactant. Everything on the left-hand side of the arrow is called a reactant, this is called a product. They assume that you have enough reactant. So, how much of this, how much water can you make from 2.5 grams of O2, excuse me, from 2.5 moles of O2? This is for gas, gas. For 2.5 moles of O2, how much water, how many moles of water can you make, assuming you have enough hydrogen? So, what do you use to convert from moles of O2 to moles of water? It's this relationship. For every mole of O2, for every 6.022 times 10 to the 23rd molecules of O2 you put in, you're going to get twice that many, 2 times 6.022 times 10 to the 23rd molecules of water. So for every 1 mole of oxygen you put in, you're going to get 2 moles of water. Okay? All right. So that means we need a relationship. And the relationship is this, that for every 1 mole, again, spell mole without the E on the end. For every 1 mole of O2, that equals 2 moles. You're going to be able to produce 2 moles of H2O. Okay? So it means that this amount equals this amount. Now there's 2 ways you can write this. You can write it like this. You can say for every 1 mole of O2, there's 2 moles of H2O. Okay, that's what this ratio means. It means 1 mole of O2 is the same as 2 moles of H2O. You could also say it the other way around. 2 moles of H2O, there are 2 moles of H2O for every 1 mole of O2. So these, I'm going to put an or between them, and these are actually equal to each other. So there are 2 moles of H2O for every 1 mole of O2. That's what this equation is telling us. We get 2 moles of H2O for every 1 mole of O2. Or we can simply say that same sentence backwards. It takes 1 mole of O2 to give you 2 moles of H2O. And these ratios express that. Now you may say, wait a minute, in math class, I can't just take the number 1 over 2 and say it's the same as 2 over 1. You can here because there's units of measure attached to it. You're saying what the 1 means exactly. It means moles of O2. You're saying what they're not just numbers. It's not just the number 1/2 and the number 2 over 1. So you're saying 1 mole of O2 for every 2 moles of H2O, or it's just as valid to say 2 moles of H2O for every 1 mole of O2. So now you have to ask yourself a question. You're starting off over here with 2.5 moles of O2. That's what they gave you to start off with. You need to pick one of these two ratios to make moles of O2 disappear and moles of H2O appear, because that's what they're asking you for. How many moles of H2O? So you have to use one of these two ratios. Which one do you have to use? Now this is a math question. Well, you want the one that makes moles of O2 cancel out and moles of H2O to appear on the top. So if I use this one right here, then moles of O2 is on the bottom. So moles of O2 cancels with moles of O2. And what I have left at the end of that cancellation is moles of H2O, and I call that the last man standing. It's the last unit of measure standing, is moles of H2O. So you had to pick the one of these two. Both of these are true statements, but only one of them helps you to solve the equation. You needed to pick the one that makes moles of O2 cancel out, which this did here and here, and make moles of O2 appear in your final answer, because that's what the question is asking you for in the answer. How many moles of H2O? And so now that you've set up the equation properly, you multiply everything on the top, 2.5 times 2 gives you 5, and then you divide by everything on the bottom. 5 divided by 1 is 5, so the answer is 5 moles of H2O. Now this one's simple enough that you can just kind of look at it and see, yeah, that should be the answer. Why? Because you see that you're going to get twice as much water, twice as many moles of water as you started off with moles of O2. So if we started off with 2.5 moles of O2, we're going to end up with twice that many, 5 moles of water. Okay? First this might seem a little hard, but you do enough of these and they'll start to come through. Okay, let's do the next one. First of all, I'm going to erase these numbers because I want to reuse these boxes up here. So do that. Just write them really lightly in pencil, because you're going to want to use this graphic organizer over and over again. Next, how many moles of H2O? So again, we're going to put a question mark where we had it before, because it's asking us for moles of H2O. How many moles of H2O can be made from 0.37 moles of H2? So again, we're in the moles area up here inside the chemical equation, and it's starting us with 0.37 moles of H2. So I put 0.37 moles there. Okay? All right. Now, I got to set up a relationship between moles of H2 and moles of H2O. And I see that there's 2 moles of H2 for every 2 moles of H2O. So I'm going to write that out here. 2 moles of H2 equals 2 moles of H2O. In other words, if I put in 2 moles of hydrogen, assuming that I have enough oxygen to make this reaction work, if I put in 2 moles of hydrogen, I'm going to end up with 2 moles of water. Now it's called a 1-to-1 relationship. Why is it called 1-to-1 even though that's a 2 and that's a 2? Because what it really is saying is that for every 1 mole of hydrogen, I get 1 mole of water. For every 2 moles of hydrogen, I get 2 moles of water. I could keep going. For every 3 moles of hydrogen, I get 3 moles of water. So that's called a 1-to-1 relationship. It means you need 1 mole of this to match up with 1 mole of this, okay? So 2 to 2 is the same as saying 1 to 1, but I'm going to go ahead and write this as 2 to 2. So here we go. So 2 moles, I can say that for every 2 moles of hydrogen, there's 2 moles of hydrogen gas for every 2 moles of water. Or it's also true to say that there's 2 moles of water. This is a true statement also. For every 2 moles of hydrogen. Okay? Those are both true statements. There's 2 moles of hydrogen for every 2 moles of water that we get out, or there's 2 moles of water for every 2 moles of hydrogen that we put in. Okay, the same thing, both true. Now, we said we're starting off knowing that we have 0.37 moles of H2. So there's 0.37 moles of H2. And it's asking us how many moles of water. So we're trying to get to how many moles of water. So that we don't know this number yet. So which of these two is going to make moles of H2 cancel out? Because we don't want moles of H2 in our final answer. We want moles of H2O. We want moles of H2 to cancel out, and we want moles of H2O to appear on the top of the ratio so that it appears in the final answer. So which of these two ratios does that? Think about that for a second. And the answer is, you can see it right there, it's this one right here. So if I have 2 moles of H2O on the top and 2 moles of H2 on the bottom, the moles of H2 on this right here cancels out with the moles of H2 down on the bottom. So they cancel out, just like fractions, just like numbers in math, okay, or variables in math. What you're left with is moles of H2O on the top, which is what you want your final answer to be expressed in, is moles of H2O. I call that the last man standing, because after you canceled out everything you're going to cancel, you still have this 1 unit of measure left, and that's what your final answer is going to have in it. So now that we have the equation set up properly, we do the math. 0.37 times 2, you multiply everything on top. By the way, you may be asking, this doesn't have a top or a bottom to it. If it doesn't have a top or a bottom, it's on the top. You just assume it's 0.37 moles of H2 over 1 if you wanted to make a fraction out of that, okay? So yes, this is on the top. So 0.37 moles of H2 times 2 divided by 2 gives you 0.37 moles of H2O. So the numbers stayed the same, but the unit of measure, moles of H2O, changed. Okay? And if you look up here, that makes sense. If you put in 2 moles of H2, you're going to get 2 moles of H2O. If you put in 0.37 moles of H2, you're going to get 0.37 moles of H2O. If you put in 47 moles of H2, you're going to get 47 moles of H2O. That's what's meant by a 1-to-1 relationship. Okay, now we're going to get into one that's more complicated. In fact, I jumped to one that's the most complicated really quickly. First of all, again, let's erase these numbers because we're going to use this. And now this is where the graphic organizer helps you to kind of keep a roadmap. It's asking how many grams of H2, so the how many means that's our unknown, grams of H2 are needed to make 3.76 grams of H2O. Should have a question mark there. Okay, so what do we not know? Or what are we trying to find out? Grams of H2. So I come up here, here's the H2 column, and now we're out in our world, okay? We've just measured, or we want to know how many grams we're going to need to make a certain amount of water. So we're in grams, and we're below H2, and that's our question mark. We're trying to find out how many grams of H2, that number right there, are needed to make 3.76 grams of H2O. So again, we're in the grams row down here. This is our world. This is something we can weigh on a scale. And we're under the H2O. We're in the H2O column. So I'm going to put 3.76 here. And that's in grams because it says it's in grams right there. Okay? So what we're saying is this. What is this question asking in the lab? You in the lab measured, you performed this reaction, and you measured 3.76 grams of H2O. Or you want to make 3.76 grams of H2O. Let's say that. You want to know how much hydrogen, assuming that you have enough oxygen, because oxygen is not involved in this question. Assuming that you have enough oxygen, it won't run out. You're going to want to know how many grams of hydrogen of H2 gas you're going to need to start with in order to make 3.76 grams of water. Now, you're not allowed to jump directly from here to here. There's no way to do that. That's grams to grams. There's no way to relate the mass in grams of H2 to the mass in grams of H2O without going through the chemical equation. That's our recipe, okay? Just because I give you 52 eggs and 32 pounds of flour and 10 pounds of sugar doesn't mean you know how to make a cake with that unless I give you the recipe for the cake. So you need the ingredients, but you also need the recipe. So these are the ingredients we're working with. This is the recipe. So how do we get from here to here? You move, it's a 3-step process. You move up and you figure out how many moles of H2 you have. Then you move across and you compute how many moles of water that would produce. And then once you have moles of water, you come out through this translator right here to get 3.76. Here's the thing though, we're actually moving in the other direction. That's the way the reaction would work. But mathematically we're going in the opposite direction. Why? Because we're starting with what we know and we want to end with what we don't know. That's what you always do in a math equation. We're starting that we know we want 3.76 grams of water. We want to know how much hydrogen that would be. So I'm actually going to move this way, across this way, and down to here. Okay? So from here to here, here to here, and here to here. Okay, so the way you do this is... Okay, so how do you do this? Looks like a lot to unpack here. So let's start off. I'm going to cover up everything here that you don't know. Here's all you know. You know you're trying to find how many grams of H2. So you put that way over on the right side. You're starting to build a math equation here. You put grams of H2 because that's what you're trying to find out, how many grams of H2. You put that way over on the right because that's where you always put the answer to a math equation. And then what you're starting off with that you know is 3.76 grams of H2O. So you put that way over on the left. And then in between, you're going to fill that in with conversions, okay? And I'm going to write the conversions on this card. So the first one we need is we need to convert from grams of H2O to moles of H2O, and there's our translator right there. There's 1 mole of H2O for every 18.02 grams of H2O. Okay, so that means I can make 2 ratios out of that. I want to say that I have 3.76 grams of H2O, and I want to convert that into moles of H2O. Okay, so I need a conversion between grams and moles using this. So I can either say that there's 1 mole H2O over, so I'm writing the same kind of fractions that I did here. So I'm not going to write them out, I'm just going to tell you what they are. I can either say there's 1 mole of H2O over 18.02 grams of H2O, or there's 18.02 grams of H2O for every 1 mole of H2O. Well, I'm starting here with grams of H2O. I want to get to moles of H2O. So which one of these 2 things do I want on the top and which one do I want on the bottom? Well, whichever one you're trying to get to, you want that one on the top. So what I want here is I want 1 mole. This should be up here. Let me actually write it. So I'm going to say this is times 1 mole H2O for every 18.02 grams of H2O. Okay? So the math here is grams cancels of H2O cancels with grams of H2O, and I end up with moles of H2O right there. And that's what I'm going to end up with, that number right there. So it would be 3.76 times 1 divided by 18.02. Now here's the thing. You don't actually have to solve that problem and write it up there. I'm going to do it this time though. I think I should. Okay, so here we go. So if I did that, that would give me 3.76 divided by 18.02. And that gives me 0.21. So I'm going to write that here. So that's how many moles of H2O I have. Okay? And What you do, though, is you write this. When I was about to say is you don't do each calculation, each step, but I'm going to do it this time. What you do is you simply write that ratio right here. So 3.76 times 1 mole of H2O for every 18 grams of H2O. The grams of H2O cancels and I have moles of H2O. But you don't have to solve the equation quite yet. So next conversion we have is from moles of H2O to moles of H2. And we already did this one. We saw that for every 2 moles of H2O, we have 2 moles of H2. So this one we did up here, right? This one right there. So if we have 0.21 moles of H2O, that means we're going to have 0.21 moles of H2. For every one of these, I need one of these. For every 2 of these, I need 2 of these. For every or the other way around, for every 2 of these, I need 2 of these. For every 0.21 moles of H2O I want to make, I need to start out with the same amount, 0.21 moles of H2. So it's that 2 moles of H2O to 2 moles of H2. Except this time, which of these two are we going to need? We need moles of H2O to cancel out. Why? Because it's not in our final answer. We're interested in grams of H2, not moles of H2O. So what that tells us is we need moles of H2O to cancel out. So what I'm going to do is slide the card over. And you can see I used one of these two ratios, but you'll notice it's a different one than I used for this problem. Why? Because it just has to do with which units I need to cancel out. So over here it was 2 moles of H2O over 2 moles of H2, whereas this one I'm doing 2 moles of H2 over 2 moles of H2O. Again, you may still be saying, why? Because I need moles of H2O to cancel with moles of H2O. Okay? So what that does is it gives me 0.21 moles of H2 right there. 0.21 moles of H2 right there. Now I'm only one step away from getting my answer. I need to convert 0.21 moles of H2 into some number of grams of H2, and that will answer the question I've been asked, how many grams of H2? So here's my translator between moles of H2 and grams of H2. It's this right here, 1 mole of H2 equals 2.02 grams of H2. So let me go ahead and write that equation down here. So 0.021 moles of H2 times something is going to equal some number of grams of H2. So I have this conversion right here, so I can either write that, see if you can do this on your own. I can either write 1 mole of H2 for every 2.02 grams of H2. Okay? That's this right here. Or I can put the other one on top. I can say 2.02 grams of H2 for every 1 mole of H2. Okay? So which one of these two do I want to stick up here? And the answer is, I want moles of H2 to cancel out and grams of H2 to appear on the top of the equation. So I'm going to use this one. So I'm going to be times 2.02 grams of H2 for every 1 mole of H2. So moles of H2 cancels with moles of H2, and the last man standing is grams of H2, which is what I want. And if I multiply those numbers, I get 0.42 grams of H2. Okay, but what I did was, rather than again work this as a separate equation, I took this conversion right here and I put it in this equation. Oops. Put it in this equation right there. So 2 grams, it should be 2.02 actually, for every 1 mole of H2. And so what I did was I took 3 different equations, and wrapped them all into one big equation. So let's see if it cancels. Moles of H2 cancels with moles of H2. And what do I have? The last man standing is grams of H2, and that's what I want my final answer to be in, is grams of H2. So notice how everything canceled. This cancels with this, the units. This cancels with this. This cancels with this. You're left with this. So now that you have the units lined up, so you end up with the units you want to have for your final answer, it was asking us for grams of H2, you multiply 3.76 times 1 times 2 times 2, divided by 1, divided by 2, divided by 18.02 it should actually be. And that gave us 0.42. And that's the answer there. Thing you're going to be asked today, this week. Alright, so the following 2 pages, you can go ahead and work those if you want. Those are going to be for Monday, actually. So we got one more question relating to this same equation and same information set. How many grams of O2? So it's asking you to find some unknown number of grams of O2. You're trying to find that out. So let's go ahead and do that. What are we looking for? Here's the O2 column, and we're down here in the grams row. That's our world. So they want to know how many grams of O2 do we have to measure out. So I'm going to put a question mark there. It's asking us for that. How many grams of O2 are needed to make 7.41 grams of H2O? So we want to end up where, when we're done with our experiment, we take the H2O that's in a beaker or a flask, and we have 7.41 grams. So this is our known. We know that's what we want to end up with. We want to know how many grams of oxygen we need to put in. Okay. If I tell you I want you to bake 100 cakes, I'm telling you what I want you to end up with. Then I'm going to ask you, well, how many cups of sugar do you need to make 100 cakes? Well, I need to give you some more information to do that, and you need to have the recipe, and there's the recipe up there. If I told you needed 2 cups of sugar for every cake, then you would know I need to make 100 cakes. I need 2 cups of sugar per cake. That means I need 200 cups of sugar. Okay, so that's what this is. This is the recipe. All right, so it's asking us, assuming, and we always assume you have enough of the other reactant. So H2 is not involved in this question. You assume you have enough of it. You're not going to run out of it. Then if you assume you have enough of this, how much oxygen will you need? How many grams of oxygen will you need to be able to produce 7.41 grams of water? Okay? So how do we write that in our equation down here? We look at the bottom. Way over on the right-hand side, because that's where you want your answer to be, we put grams of oxygen. We don't know the number yet. We're not there yet. That's what we're trying to figure out. On the right-hand side, we start with what we know. We know we want to end up with 7.41 grams of H2O. So we put that way over on the side. And now we're going to do our conversions to get from here to here. So let's see if you can answer this question. How many different conversions are you going to need to do to get from here to here? Okay. Well, if you could go directly from here to here, or really I should say mathematically from what you know to what you don't know, it would be 1. But there's no way to do that. You can't convert from grams to grams because we don't know the relationship. So what you have to do is this. One conversion takes you up and gives you moles of H2O. The second conversion goes from moles of H2O to moles of O2. And the third conversion comes back out using this translator right here. This molar mass goes from moles of O2 to grams of O2. And that's what the question is asking for. So there's 3 conversions. Okay, so I'm not going to write out each one of these as separate equations like I did on the last one. That actually maybe makes it a little harder to understand because it just seems like there was so much writing. So here's what we're going to do. First of all, we need to get from here to here using this. So we need to get from grams to moles. So we need grams to disappear, grams of H2O to disappear, and moles to appear. So which one of these 2 ratios will do that? 1 mole of H2O over 18.02 grams of H2O, or 18.02 grams of H2O over 1 mole of H2O. Remember, we want to end up with moles of H2O when we get to this step. Well, It's the one that has moles of H2O on the top. That's what you want to end up with here. So grams of H2O has to cancel out because that's something we want to go away. That's what we started with grams of H2O, but we want that to disappear. So right here I'm going to slide my card over, and there it is right there. So I have 7.41 grams of H2O times 1 mole of H2O for every 18.02 grams of H2O. So grams of H2O cancels with grams of H2O, and I have moles of H2O, and that puts me in this box right here. I'm not going to write out the number. I'm not going to do the calculation. We don't need to. We do all three of the calculations at the same time. Now we need to go from moles of H2O to moles of O2. We need to move from here to here. So we can either say that there's 2 moles of H2O over 1 mole of O2, or there's 1 mole of O2 over 2 moles of H2O. Which one do we want? Well, we're trying to get from here to here. We're not interested in moles of H2O. We need to get over to moles of O2. So that's what we want to be on the top of our fraction. So we want 1 mole of O2 over 2 moles of H2O. So I'm going to slide the card over, and there you see that right there. 1 mole of O2 over 2 moles of H2O. Okay? So that means the 2 moles of H2O cancels there and there. See how everything's canceling out that I don't want to have as part of my final answer? Move this up a little more. Okay, so now we don't really care what this number is right now. We just care that we can get from here to here. We care about this number. So we need to get, I'll move this back and forth, from moles of O2 to grams of O2, and that's what our final answer is. It's how many grams of O2 is what we're trying to find out. So let's move this back. So we see that we have 1 mole of O2 over 32 grams of O2, or 32 grams of O2 over 1 mole of O2. We're trying to make moles of O2 disappear and grams of O2 appear in our final answer. That's what we want to know. So which one goes on top? The one that you want to know is the one that goes on top. So we want grams, 32 grams of O2 over 1 mole of O2. And so I slide my card over one more time, and I have 32 grams of O2 over 1 mole of O2. And again, the way you know how to set this up is they should cancel out. And the only thing you should be left with at the end is grams of O2, because that's what we said we want for our final answer. We want to know how many grams of O2. So we see all the units have canceled out. That means we've set up the problem correctly and ended up with the correct units at the end, grams of O2. So now what you do is you multiply 7.41 times 1 times 1 times 32, and then divide by everything on the bottom. Divided by 1, divided by 2, divided by 18.02 grams for water, and that gives you your answer, which is 6.59 grams of O2. So what you're saying is that you need 6.59 grams of O2 to produce 7.41 grams of H2O. Again, don't lose sight that this is just like cooking. It's just like a recipe. How many cups of sugar do I need to make so many cakes? Or if I want a certain number of cakes, how many grams of sugar am I going to need? Or how many cakes can I make if I have a certain number of grams of sugar? There's all kinds of ways you can kind of think about this, but it's just like cooking with a recipe. Okay, 50 minutes. So divide that by 2. That's 25 minutes a day, 25 for Thursday, 25 for Friday. The only thing I would like you to do on a piece of lined paper is write this out. Watch it and write it out, just this one problem, nothing from the previous page or two. And the ones that you see after this is what we'll do on Monday, okay? You see 2 more problems. Don't worry about those today. Just do this one. Try to understand how these conversions work. And that's it. Again, if you go back to an earlier time in this video, you can see all of this without all the lines and markings on it, so you can see it more cleanly, or you can just print this out if you want, or just do it on line paper. Just write it up. When you do it on line paper, I would like you to do this as well. This is an important part of learning how to do this. Okay, I hope you all are doing well. I hope your families are doing well. Take care of them. Take care of yourselves. And remember, I'm around. You can always email me or call me. You should have everything in the syllabus. And I did a Zoom meeting this morning for periods 3 and 4. I didn't get anybody to show up. I'm going to start making those required starting next week. I'll talk to you about that more and communicate with you about that. So anyway, have a nice weekend, and I'll talk to you again on Monday.